doing indirectly in some of the earlier sections. So to find the domain of a rational function, and a rational function will have the form f of x is equal to p of x divided by q of x, where p of x and q of x are polynomials, we set q of x equal to 0 and solve to find the zeros of q. The zeros of q of x are the x values that are removed from the domain. So to find the domain of a rational function, f of x equals p of x divided by q of x, where p of x and q of x are polynomials, we set q of x equal to 0 and solve to find the zeros of q of x. The zeros of q of x are the x values that are removed from the domain. So, as a convention, when we're talking about rational functions, it will always be a polynomial divided by a polynomial. If we're talking about the polynomial p of x is the polynomial that is in the numerator of the rational function. Q of x will always be the polynomial that is in the denominator of the rational function. So when I talk about q, when we're talking about rational functions, we're talking about the one that's in the denominator, or the polynomial that's in the bottom of the fraction. All right. So now that we're equipped with that, we are ready for example number 1. So example 1 says find the domain of f of x equals x divided by x squared minus 6x plus 8. Okay, so according to this, we need to identify our q of x. So q of x is the polynomial that is in the denominator. And to find the domain, we need to set q of x equal to 0 and solve to find its zeros. So we're going to solve q of x, so x squared minus 6x plus 8 is equal to 0. So we need to solve this equation. So it's a quadratic, and it's going to factor. So what are our factors of 8 that give us -6? Well, 8 has factors 1 and 8 and 2 and 4. So we're going to end up with this. So this factors into x minus 2 times x minus 4 is equal to 0. So then our two solutions by the zero product rule, well, what makes x minus 2 equal to 0? Well, x would have to be 2. And what makes x minus 4 equal to 0? 4. So our two solutions are x equals 2 and x equals 4. So according to this, these are the zeros of Q of x. They must be removed from the domain. So these are excluded from the domain. So the zeros of Q of x are removed from the domain. So if we did that on a number line, we have everything, and then we have our zeros at 2 and 4. So these are our excluded values. So then our domain would be the three parts from negative infinity to 2, unioned with 2 to 4, unioned with 4 to infinity. So that's going to be my domain for this. Because if I remove 2 points from a line, if you think about a line as being a piece of string, if you cut a string twice, it's going to break it into 3 parts. So, all right, so to find the domain for our u-try, we identify our q of x, which is 3x minus 8, and we need to solve 3x minus 8 equals 0. Well, this time it's a linear equation, and we solve linears by just getting x by itself. So we add 8, we add 8, so we get 3x equals 8. We divide by 3, and we get x is equal to 8/3. So that's our one excluded value. So on our number line, we have the point 8/3, and we're going to exclude it. So we're going to go from negative infinity to 8/3, or from 8/3 to positive infinity. And that would be our solution to that problem. All right. So now we need another definition. So if we have a rational function, so if f of x has the form p of x divided by q of x, where p and q are polynomials, then the vertical asymptotes are the solutions to q of x equals to 0, which is the same as the zeros of q of x. Okay, so turns out that these points are related to the ones we were just finding. When we found the points that we took out of the domain, they also give rise to what are called our vertical asymptotes. So couple of things I do want to mention. So where have we seen these before? As we just said, these zeros of q of x were also what? The points that we removed from the domain of the function. So our vertical asymptotes are actually the points that are not in the domain of our rational function. So let's take a look at example 2. And we'll notice example 2 is the same problem as example 1 in the sense that we're using the same function f of x. So as a matter of fact, that means we don't really have to do any work. when it says find the vertical asymptote of this, well, we would do exactly the same thing. That's our q of x, and we would need to solve. So x squared minus 6x plus 8 is equal to 0. And we get x minus 4 times x minus 2. So our solutions are still x equals 4 and x equals 2. So then we would conclude the vertical asymptotes are x equals to 4 and x equals to 2. So those were the same two zeros of q of x. Well, let's visualize what these are by using our graphing calculator. So I want to graph this original function, f of x. So I go to my y equals, and I have x, alpha y equals to get my fraction. So x squared minus 6x plus 8. And if I go ahead and graph this thing, oh, my window's all messed up, so let me fix that. So I go zoom, choose choice number 6. And we get a picture that looks something like this. So thinking back to chapter 1, a vertical asymptote is a vertical line that we are going to graph. So vertical lines go straight up and down, and remember their x values don't change, only their y values. So if I want to graph x equals 2, I go over 1, 2, and I'm going to draw a vertical line at x equals 2. And my other vertical asymptote is at x equals 4. So I go over 1, 2, 3, 4, and I draw a vertical line at x is equal to 4. So when I look at this picture, we notice something interesting happens visually. As my graph gets close to a vertical asymptote, what happens? It either goes up to positive infinity, or it goes down to negative infinity. So my graph is always going to approach either positive or negative infinity at a vertical asymptote. So let's take note of that. The graph of a rational function will always go to plus or minus infinity at a vertical asymptote. It's also worth noting a graph can't intersect So a graph also cannot intersect a vertical asymptote. So the equation for our vertical asymptote is going to be the same as the answer you got for u try number 1, which was the point we removed from the domain. So when we set 3x minus 8 equals to 0 and we solved, we found that the point that was removed from the domain was 8/3. So that gives us that our vertical asymptote is this line. So let's go ahead and look at a picture of this one as well. So if we grab our graphing device and we graph this, we would have 5 over 3x minus 8 and we get something that looks like this. So 8/3 is 2 2/3, so we go 1, 2 2/3. It's going to be here, so that's my x equals 8/3. And we'll notice once again, as our graph comes in from the left, we see it goes down to negative infinity, and as our graph approaches it from the right, we see it goes up to positive infinity as advertised. So our vertical asymptotes act as regions that our graph can't cross, and as our graph approaches a vertical asymptote, it will always go to positive or negative infinity. All right. So I'm going to fill in an example that is in our notes to expand on what I was talking about before, just to make clear the other definition that we're not going to focus on. So I want everyone to grab their graphing device and graph this function. So if I were to have the function f of x is equal to x squared minus x take away 6 divided by x minus 3. So if we grab our graphing device, let's go ahead and plot this. So we go y equals, and I have my fraction. So I would go x squared minus x minus 6 all over x minus 3. Oops. So before I graph it, if I looked at this picture or at this function, here's my q of x. So what would my vertical asymptote appear to be? Well, what makes x minus 3 equal to 0? 3, right? So we have our domain is all values such that x can't be 3. Well, if I graph this thing, something strange appears to be happening. When I look at this picture, do I see what appears to be a rational function? No. And if I go to x equals 3 in my graph, 1, 2, 3, and I go up to the corresponding y value, it looks like 1, 2, 3, 4, 5. So my graph appears to have the point 3, 5 on it, right? Let's investigate further. If I go second table, when I go to the input 3, what does my calculator tell me the corresponding output is? Oh, error. It doesn't say 5, right? Well, why is that? Because what happens when I put 3 into the original function? 3 minus 3 is 0, and we can't divide by 0. So let's analyze this a bit further. So if I were to factor the numerator on this, I would get x squared minus x minus 6 factors into x minus 3 times x plus 2, all divided by x minus 3. then what do we notice we have in both the numerator and denominator? An x minus 3. So it would appear that our function f of x is equal to what? Well, what's left behind? X plus 2, except for, when is the one time it's not equal to x plus 2? When x doesn't equal to 3. If x equals to 3, what's the value of our function? It's undefined. So if we grab our graphing calculator and we go y equals again, let's put in our function x plus 2. And if I go second table now, what do I notice about these two functions? Their outputs are exactly the same except for at what point? At 3, I get that it's undefined in the original function, but if I look at my new function, I get that the output is defined to be 5, which is the missing point that we have on the graph. This point right here is referred to as a hole. So to make our graph correct, this is really a piecewise function with one of those hollow circles on it, like what we saw in the previous chapter. So the missing point (3, 5) is called a hole. All right, so I don't want to keep going down this rabbit hole right here, but if you ever needed to find a hole, that is how you would be able to do so. So you would simplify the function, reduce out anything you have, and then compare it to your original function. So essentially in a graph, what happens at a hole? Instead of getting a vertical asymptote, our graph looks complete. So the next thing we wish to talk about is a horizontal asymptote. So then the next thing we wish to, so horizontal asymptotes. So we need to talk about what they are. So horizontal asymptotes are the end behavior of a rational function. So we have the following for our definition. If f of x equals p of x divided by q of x, then the horizontal asymptote if it exists is given by and we're going to make a little decision chart similar to the one that we had in 4.1 for the end behavior of polynomials. So we're going to have our three possible choices. that looks something like this. So our first choice is if the degree of p of x is bigger than the degree of q of x. Our middle choice is the degree of p of x is the same as the degree of q of x. And then lastly, well, we've done bigger than, we've done equal to, is the degree of p of x is less than the degree of q of x. So then here are our possibilities. So our first one is there is no horizontal asymptote. So leave yourself a little space here because we're going to come fill something in this space right here a little bit later. So leave yourself a little bit of room. The next thing we have is if the degree of p of x equals the degree of q of x, the horizontal asymptote is the ratio of the lead coefficients of P and Q. So then y is equal to, we'll be a little more explicit in a minute, P sub n over Q sub k. And we'll talk about and remind ourselves what each of those mean. And then the last part is if the degree of P of x is less than the degree of Q of x, the horizontal asymptote is just y is equal to 0. All right, so this is our flow chart for the end behavior of a rational function or to find its horizontal asymptotes. So we have the degree of P of x is bigger than Q of x, says there's no horizontal asymptote. If the degree of P of x and Q of x is the same, the horizontal asymptote is the ratio of the lead coefficients of P and Q. And lastly, if the degree of P of x is less than the degree of Q of x, the horizontal asymptote is y equals to 0. So let's go ahead and take a look at example number 3. So example 3, we wish to find the horizontal asymptote of this. So we identify our P of x and we identify our Q of x. So P of x is always in the numerator and Q of x is in the denominator. So then we have our degree of P of x. It's going to be our exponent. So our degree of P of x is 2. And then we have our degree of Q of x is also going to be, oops, not there. Yeah. The degree of Q of x is also going to be 2. So now we look at our chart up here. So is the degree of P of x bigger than Q? Is the degree of P of x the same as the degree of Q, or is the degree of P of x less than the degree of Q? So in our case, it's going to be our middle. The horizontal asymptote is the ratio of the lead coefficients of P of x and Q of x. So we're going to be in the same way in the case where the degrees are equal. So our leading term of p of x which we're going to call p sub n, is, our leading term is 3x squared. So we have our p sub n x to the n. So that tells us then that our p sub n looks a little funny. Our p sub n is going to be 3. And we do the same thing for our q of x. We're going to have our leading term over here, but it's going to be q sub k x to the k. So we have our leading term is 2x squared, and we compare that to q sub k x to the k, and we have that our q sub k is going to be 2. So really, all we're talking about is the lead coefficients, right? So it is this value here, R2, and this value here, which is R3. So it's, don't let the definition seem overly complicated. We're really just talking about the lead coefficients. And then the horizontal asymptote is the ratio or the division of those two things. So our horizontal asymptote is y equals Pn over Qk, or simply put, it's y equals 3 over 2. So that would be our horizontal asymptote. So the key ingredient to all of this depends on the degree of the two polynomials. So essentially, if the degree of the numerator is bigger than the degree of the denominator, there's going to be no horizontal asymptote. If their degrees are the same, like what we just had, they were both degree 2, we take the ratio of the lead coefficients. If the degree of the numerator is smaller than the degree of the denominator, then the answer is just y equals 0, and that's it. Those are the only 3 things that can happen. So now for you try number 3, we want to find the horizontal asymptote. So I look at my p of x, and what is my degree of p of x here? 1. And I look at my degree of q of x, which is going to be 2. So if the degree of p is 1 and the degree of q is 2, that puts me down here because 1 is less than 2. So then my conclusion is my horizontal asymptote is y is equal to 0. And we're done. Perfect. All right. So we need another definition when we move into for our last type of asymptote. So we've done vertical asymptotes, we've done horizontal asymptotes, and there's one other type of asymptote which is called an oblique or a slant asymptote. So a rational function will have an oblique also known as a slant asymptote if and only if the degree of p of x is exactly 1 larger than the degree of q of x. So what we mean by that is that the degree of p of x is equal to the degree of q of x plus 1. So now let's go back to our little chart here. So if the degree of p of x is bigger than the degree of q of x, this happens when there is no horizontal asymptote. So we can only have an oblique or a slant asymptote if there is no horizontal asymptote. So in this one, we check if the degree of p of x is equal to the degree of q of x plus 1. If so, there is an oblique asymptote. So a graph cannot have both a horizontal asymptote and an oblique asymptote. It's one or the other. And the only time we have to worry about maybe finding an oblique asymptote is if there is no horizontal. And then it's not for all of them. It's only if the degree of the top is exactly 1 bigger than the degree of the bottom. Okay, so now we know when we are going to have oblique asymptotes, but we haven't talked about, well, how do you find one? Well, that's where our polynomial long division comes in. The oblique asymptote is the whole part without the remainder when p of x is divided by q of x using long division. So the answer is y equals the whole part. All right. We need to do our long division. So how many times does x go into x cubed? Well, that's x. X times x squared is x cubed. And x times negative 2x is negative 2x squared. X times negative 2 is negative 2x. And then I subtract. Our x cubes reduce out. And then I have minus. A minus gives me plus positive. So negative 3x plus 2x is negative x. And then I have 3x minus a minus 2x gives me 5. So plus 5x, and then I bring down my next piece, which is negative 1. And now I rinse and repeat. So how many times does x squared go into negative x squared? Well, that's negative 1. Negative 1 times x squared is negative x squared. Negative 1 times negative 2x is positive 2x. And negative 1 times negative 2 gives me positive 2. And then I subtract. Those reduce out. 5x minus a positive 2x is 3x. Negative 1 minus a positive 2 is negative 3. And now x squared no longer divides into x, so I get my remainder is 3x minus 3. So my whole part is this. So my answer is y equals to x minus 1. And that is going to be my slant or oblique asymptote. All right, so for example number 5, we're going to set up our same thing. So we have x minus 5, and we want to divide that into x squared minus 6x plus 9. So x times x gives us x squared, so x goes into x squared x times. So x times x is x squared. X times negative 5 is negative 5x. And we subtract, and those reduce out. So negative 6x minus a minus 5x is negative x. And then we bring down a positive 9. So then we ask, well, what times x gives us negative x is negative 1. So negative 1 times x gives us negative x, and negative 1 times negative 5 gives us positive 5, and then we subtract. So negative x makes it positive, so those two guys reduce out, and then 9 take away 5 gives me 4. So my remainder is going to be positive 4. But we don't even care about the remainder, so the oblique asymptote is going to be x minus 1.